And hello everybody, and welcome to another wee video. It's another wee bench test video. We're going to show a couple of wee things, do a few wee calculations, and do a couple of wee experiments maybe. Just demonstrating current flow and stuff like that. So when you're working on a car and you have bad connections, or the green crusties as people like to call them, we can maybe get a wee bit of an understanding by doing a wee bit of mucking about on the bench here. So I'll just show you this wee boy here. This is an H7 bulb in a cap. So all that is a cap of an old tin there, brake cleaner. A couple of slots in it for the prongs, a couple of spade connectors. I've soldered and heat shrink wee bits on just for reliability. A couple of bits of wire, a wee bit length. So that is just a wee bulb there, and we'll have our solder station, which we're going to use as a power supply. But the good thing about this wee solder station is it actually it's all adjustable, and it's not fixed in 12 volts, which I may have implied in another video, but it will show us a current and it's adjustable voltage. So we can see our what happens with change in voltage and current flow through this H7 bulb. So first of all, this H7 bulb here, it's rated 12 volts, 55 watts. So to work out the current, it's pretty simple. We equation here. So power equals volts multiplied by the amps. P equals VI. So dead easy. So the power here is 55 watts equals the voltage. So we're going to use 12 volts because that's a nominal voltage, and that works out that. So we need to transpose that equation. So we want to know what I is. So that's what we're trying to find out. So I equals P over V, which is the 55 divided by 12. So dead easy calculation. We'll put it in the calculator to get it accurate. Now, let me see. 55 divided by 12 comes out at 4.583 amps. So we're in around 4.5 amps with this H7 bulb, according to that, if it is indeed 55 watts. So, get that out of the way. We'll fire this baby up here and see what it says. So there's the bulb lit, and hopefully you can see that. So we're currently at 5.6 volts and it's drawing 2.78 amps according to that. So we've got our wee uni T here, and we'll select it for DC current, zero it out, and we'll put that there. If you can see that, okay. So 2.77 amps, the wee uni T is showing us, and the output of that 2.78. So it all matches up pretty well. That's pretty good. So what we're going to do is we're going to increase this to bring it up to 12 volts. So the voltage here is the top one here. So we'll bring it up to 12 volts, which is the nominal voltage that we would be using. So it's actually sitting at 4.1 and 4.11 on the uni T as well. There we go, 4.07. So at 12 volts, it's outputting about 4 amps. So the relationship between the voltage and the current, that's what we're sort of interested in here. So if I bring the current down and bring the voltage down, bring the voltage down there, 7, 6, 5 volts there. You see the lamp getting dimmer. That's a couple of amps. So it's reflecting on this. A slight discrepancy, about 0.3 of an amp. And there we go, there's only a couple of volts there. We'll bring it back up again. And we'll go back up to 12 volts again. So that one there's just a fine tuner one there that I'm using. So it's a bit of a discrepancy, but it's more or less the same. It's about 4 amps. So it's a wee bit less than the 55 watts that they're saying here, but it may not be just purely resistive load here. There's because the filament is a coil, you may get a bit of inductance, so that may explain the relationship. So there may be a bit of a power factor going on here, but anyway, what I want to explain is this relationship between the voltage and the current. So I'll just knock that off for a second, and we'll get another bit of paper out. So voltage and current, quite simply, everybody knows it. Ohm's Law, V equals IR. Okay, so what power companies sometimes do, sometimes they decrease the voltage in their network. So they bring the voltage down in a low load condition, say at night time or in the summertime or something like that. So what they're trying to do is decrease the amount of demand on the generators. So if the theory is that if we take R as being a constant, so that's a constant, the resistance you can do nothing about. So that's the load of the houses and the towns and everything that's connected to the network. So if we take R as a constant, take R out of the equation. So if you bring the voltage down, that then brings the current down. So the current is the amount of demand on the generator. So if they're transmitting at 132 kV and you bring it down to say 130 kV, then I then goes down proportionally, because it's directly proportional, because R is a constant and that doesn't change. Now in reality, R isn't a constant, but the actual load, the resistance that you have in the network, there's nothing you can do about it. So that is static as far as they're concerned, because they can't change that. So you bring the voltage down, and that brings the current down, and that decreases the demand on the generators. So V equals IR again, with what we're seeing here. We're wanting to know what current is. So current is multiplied by R. So I equals V over R. So that is indirectly proportional. So when you bring the voltage up, so you bring the voltage up, the current goes up. But what we're interested in the case of when we have high resistance or a floating resistance, when you bring the resistance up, then that actually brings the current down, because it's inversely proportional. So I equals V over R, that is inversely proportional to current. So in the case of the automotive, if the voltage is 12 volts, the voltage is static in this case, whereas this case here, you're changing the voltage. The voltage is the same here, but the problem with our green crusties is the resistance goes up, and that actually brings the resistance down then, or the current down, I beg your pardon. So when we do a wee experiment here, a wee bench test, we'll try and make a variable resistor and simulate what we would have if we had bad connections or green crusties or poor connections on the automotive wiring, and see what effect that has on the current by putting a load on it. That's the key thing. You need to put a load on it. So this thing here pulls 4 amps, and whenever we do that, I'm shouting at me there to turn off. Whenever whenever we put a load on it, we'll see what effect that has on the current. So that'll tell us why modules don't work or sensors don't work if we have this increase in resistance here due to poor connections or water ingress or rotten wiring. Okay, so I'll just change what I have in the bench here, get rid of this, these wee equations, and back in a sec. So here we are, we'll have a piece of C channel, which I found out the back there. So it's quite rusty, and it's going to give us a varying resistance here. So resistance all over the place, just depending on the, it is mild steel, normally be a half decent conductor, but it's because it's all rusty, we're going to get bad connections here. So this is going to simulate our bad connections in our car, or green crusties, or poor wiring. So as we can see, when we move it about there, I'm getting a few thousand ohms, depending on where I put it. So what we're going to do is connect this to a car battery. I have a car battery on the floor here, just below the bench, and we'll put it through our H7 bulb. We'll see the change in the current on the wee Uni T. Okay, so we've just connected to the car battery, and if we do a good connection there, we're getting the 4.1 amps from our H7 bulb there on the Uni T. So we're going to connect it to our resistor here and just scoot it about. There we've lost a good half an amp there, and we'll move it about. You can see the sparks flying as we do that. So this is our bad connection, and there's your load or your sensor or whatever it is. Get one open circuit on us, and yeah, so there's about, we'll get it to about half an amp of loss because of this additional resistance. So yeah, there's about 3.8 amps. That's only about 0.3. Yeah, 3.6. So what we can do then is one of these wee thermal imaging cameras. If I leave that, go in there for a wee minute or two, we can see our bulb is about 40 odd degrees there, and we'll have a wee look at this. If we can get the glare out of that. That's that crocodile clip there. This crocodile clip here, we can see that is a bad connection. There's high resistance there, so we're getting a bad connection. That it's 18 degrees, so not good. And that's how we get problems on our cars. So there we go, that's 17, 18 degrees. So we've introduced that bit of resistance there, and it's actually warm to the touch now. So there's 3.6. So resistance makes the current go down, and when there ain't no current flowing, the sensor or the load or whatever it is gonna struggle. That's an open circuit completely. 3.7. Okay, so that's it for this one. I hope you enjoyed that wee bit of experiment, wee bit of bench testing, and what effect the green crusties and the bad connections have in the car with water ingress and rust and poor connections on your grounds and your body, or anywhere at all, in fact. So If it goes open circuit completely, no current flowing at all, but if there's resistance, it impedes the current to flow, so therefore your whatever it is you're wanting to work doesn't work. Simple as that. So yeah, so you can do this with you can test voltage and see the voltage dropping because of this, but I'm just demonstrating this one with current flow. So I hope that helps somebody. Hope somebody finds it interesting. I'll have to take all this down now, but thanks for watching as ever, and all the best. And we'll be posting another video soon, I'm sure. So thanks very much again. All the best. Bye bye.